Uh, so we were at implicit methods and we were trying to find out the convergence criteria for implicit methods. So our ODE was dH by dt plus CH is equal to 0. Now if I do the implicit discretization of this equation, then Hn plus 1 minus Hn divided by delta t is nothing but minus Chn plus 1. That essentially means Hn plus 1 is equal to Hn minus C del t Hn plus 1, which means 1 plus C del t Hn plus 1 is equal to Hn. This implies Hn plus 1 is nothing but Hn 1 plus C delta t. Now since 1 plus C delta t is greater than 1. Now how am I saying this? So 1 by C is tau, which is time constant. This implies C is always greater than 0. Since t is time, so time will obviously be positive. That means 1 by C will also be positive. That essentially means that C will be positive. This implies C delta t will definitely be a positive number, and if C delta t is definitely a positive number, then 1 plus C delta t will definitely be greater than 1. So that means Hn plus 1 is equal to Hn 1 plus C delta t, and we know that 1 plus C delta t is greater than 1. This essentially means 1 plus C delta t is greater than 0, which means this equation will definitely converge. So there is no constraint over delta t. That means implicit methods are unconditionally stable. So it's as simple as that. No divergence problem in implicit methods. So let me write down few statements about these. That the first statement is that implicit method are unconditionally stable, and so is the Crank-Nicolson method. So Crank-Nicolson method is also unconditionally stable or unconditionally converges. Second point is that explicit methods are conditionally stable, and the condition is that my delta t should always be less than 1 by C, and usually we take delta t to be equal to 0.1 times tau, or 0.1 times 1 by C. My third point is that explicit methods approaches the exact solution faster then the implicit methods, but condition for stability must be satisfied. Fourth point is that due to this stability criterion, implicit and Crank-Nicolson methods found favor over explicit method. So usually people are using implicit formulation or the Crank-Nicolson formulation because there is no condition on its convergence criteria or there is no condition on stability. So last topic which I want to teach you guys in these initial value problems or ordinary differential equations or first order ordinary differential equations is the time constant. We have already discussed about it, but let us talk about it one more time. So the next topic is time constant. So usually delta t is taken as 0.1 times tau. For explicit, here tau is time constant. So how to calculate the time constant is dy over dx plus cy is equal to f of x. So this is my linear ODE and the time constant for this will be tau is nothing but 1 by c. Now remember, this is linear ODE. So suppose if there is a nonlinear ODE, then we will have to linearize it first to calculate the time constant. This implies to get the time constant, of nonlinear ODEs, we will have to linearize it first. So I'll give you few examples. That first example is dh over dt plus h is equal to 0. Here time constant tau is 1 upon 1 is equal to 1. Example number 2, dh over dt plus root h is equal to t. What is the value of tau? Now since this is nonlinear, so first we will have to linearize this. Linearization will become t root of h naught plus 1 upon 2 root h naught h minus h naught is equal to 0. This makes it dh over dt plus 1 upon 2 root h naught h is equal to minus root h naught divided by 2. So for this tau becomes 1 upon 2 root h naught. Tau is 2 root h naught. So this time constant depend upon h naught or h tilde. So we can write that tau is 2 root h tilde. So time constant will depend upon the initial value of h tilde. You know, when we are solving this, we need to take the initial guess. So my time constant will be a function of initial guess, or within each time step my time constant will be the function of initial value, that is either the initial value or the value coming out from the previous iteration, sorry, from the previous time step or previous iteration. So this is how the tau will change at each time step for this second nonlinear ODE. And remember that to get the time constant we need to linearize the ODE first, then whatever is the constant of h or y, 1 upon that constant will become the time constant. So here we end this video. Thank you.